There's two aspects to this project. One is a physical study about the feasibility of using recycled material, particularly using thin-walled irrigation drip tape that's typically a single-use product, and reprocessing it into thick-walled drip tape, which is a long-term product. We're taking plastic that's already in the irrigation stream and turning it into something that was a single use into a long-term use product. The other aspect of this project is an economic study. And that's where the innovation lies, was that having these recycling operations is inherently limited by distance and limited by the relative price of new resin. The premise is that for recycling to be feasible, there has to be somebody local who knows where their single-use strip tape is being used, it has the resources to go and pick it up, and can transport it back to the production facility where it gets turned into new thick-walled tubing.
Drip irrigation provides incredible and significant benefits for growers around the world, but that drip tape goes to a landfill. Many of those environmental benefits would be offset and negated. So it's really important to me personally, for our company and our management and our staff, to ensure that we have a long-term viability of this amazing drip irrigation technology. In summary, we're pretty excited about that. This could take over 100 million pounds of single-use plastic from going to a landfill each year in the United States. It's really only coming together due to the work that the IIC is doing.
I'm interested in the irrigation research that the National Renewable Energy Laboratory is doing here, because I think that's going to help our site for better learning how much or how little water we need to put on crops around our plants that we grow out here.
A major goal of ours is to understand the trade-offs between how much water we might be saving compared to the changes in vegetation performance. We might see an increase or a decrease in vegetation performance depending on where that vegetation is in relation to the shade of the panel. This project is innovative for a few different reasons. One, this is the largest agrivoltaic research site in the entire country. Two, this site has not only crop production happening underneath it, but also pollinator habitat and native vegetation, as well as pasture grass that allows us to better understand the impacts of this partial shade on vegetation performance of different type, as well as on irrigation needs.
My hope is what we learned here at Jag Solar Garden will not only help us in growing crops better underneath our solar panels, but also help out other farms across the county as well as the state in figuring out more so of how much water is necessary for growing different types of vegetation.
The overarching goal of this project is to take a step towards center pivot automation. If we can move towards automation, then that could really reduce the labor requirement, and so we're excited about that. The overall goal of this project is to advance the technology in order to reduce the amount of water that we're using for irrigation. This project is innovative for a couple of reasons. I'm excited because this is a step towards automating center pivot irrigation systems. We are mounting sensors on the center pivot itself. We're taking advantage of the center pivot as a moving platform that already moves throughout the field and using that to collect data about the crop canopy. If a producer's not limited on the amount of water they can pump, it's really easy to put on some extra water as a cheap insurance policy to make sure they get a good yield. However, if they had more sensors and data available, they might be more confident pumping less water for irrigation throughout the year.
Been shown for a long time that soil moisture probes in the ground can save water. However, the adoption of those has really been stagnant around 10 to 15% for several decades, according to farm and ranch surveys. And so we have a problem with basically how do we scale up that kind of technology. And so this project wanted to look at basically, can we use remote sensing technology and still get some of the water savings that we would see with soil moisture probe technologies, and how can we use technology and actually transfer that to be scalable and adoptable by actual farmers on the ground is really important. I mean, actually put some of our research into action. Partnering with Darren Rudnick and through the TAPS program is a great way to do these side-by-side comparison projects, as well as get more exposure. More producers are going to be willing to take up this technology and invest it to see that there is an actual rate of return on putting some of the practices into use.
What we're trying to do is establish a straightforward way that we can estimate water delivery from electrical power consumption and electrical run time of center pivots. On a daily basis, we're collecting electrical run time on 15-minute intervals on every one of these wells throughout the year. And then using well calibrations, that's what we're doing here today, we're able to estimate water delivery. And the purpose of the project is to establish the accuracy of an approach like that, because it has the potential to establish water delivery across an entire region. So we're collaborating with public power companies, Page Wireless, GISC, Nebraska Water Balance Alliance, and cooperation of the growers.
So growers try to really make themselves more efficient, and obviously with that comes a magnitude of data that is sometimes insurmountable. That data can and possibly be used against them in some instances, and so they're very hesitant about sharing it. The great thing about this data is that we keep it very private. It really helps us to help them better themselves in the long run. The data that we bring in can show a lot of discrepancies and positive things about what they're doing with their irrigation management systems.
Having more information just helps people make better decisions. If a farmer can have up-to-date daily information on not just his power consumption, but his water usage, that would be valuable, particularly if he's operating in an area where water is somewhat limited.
What we do is we research soil moisture with our soil moisture stations that are wirelessly controlled. Part of the reason that this project is so innovative is the technology that we use, trying to keep the cost as low as possible. Also trying to keep the sensors measuring the environmental parameters close to a research grade sensor. We've been exploring over the last year as founding a company, and so we have Soil Signal is the name, and we do a lot of the work that we did in the lab, but this time we're kind of trying to outsource some of the hardware fabrication and things of that nature, so that the more people can get their hands on things that we use. Also, although we make our own sensors, we want to be able to use as many as possible. And so research grade sensors, things that already exist on the market, we always try to keep compatible with whatever we're doing. And so this year we focused primarily on improving the hardware, just making the experience a little bit easier and more streamlined.
Today, fertilizer comes from a factory 1,000 miles away from the farm in the Center for Irrigation and Technology farm in California. Fertilizer production today uses one major chemical process called the Haber-Bosch process that consumes coal or natural gas and leads to considerable greenhouse gas emissions from the form of CO2, methane, and other forms of greenhouse gases. And so we use a process that's similar in nature to lightning. Lightning can break down nitrogen in air, and rainwater can scrub it from the sky. We've done that, but we've packaged it in a system underneath the solar array using a novel process into liquid, so water-soluble nitrate-based nitrogen, and then sent it out through irrigation to the field. We're trying to increase the size of the hardware by a factor of about 20. From what we first tested at Fresno State to what we're testing now on a commercial farm nearby. And so our solar array is much larger. Working with Fresno State and specifically the director, Dr. Charles Hillier at CIT, was really important to help us understand what needed to happen to scale this and which key challenges that we had to overcome. And 2021, we are still working on the development of a much larger system tied to a standard irrigation set size